Have you ever wondered how a computer plays a game like chess? Or even something as simple as tic-tac-toe? I mean, it doesn't just make random moves, right? It seems to have this uncanny ability to see 10 steps ahead. Well, today we're going to pull back the curtain and look at the fundamental logic that gives an AI its winning edge.
All right, so let's start with a puzzle. Here we have Max who's playing X's and Min who's playing O's. Now it's Max's turn, and if you look at the board, she can easily block Min from winning on that top row. Seems like a no-brainer, right? A totally simple move. But look at Max. She's got her head in her hands. She looks like she's already lost. The question is, what on earth does she see that we don't?
Okay, to get to the bottom of this, we have to stop thinking like we normally do. Just looking one or two moves ahead. We need to shift our perspective entirely and try to see this game the way an AI would.
You see, an AI doesn't just see the current board. Not at all. It sees this massive, sprawling map of every single possible future that could happen from this one moment. We call this map a game tree. And on this map, every single point, or node, is one possible version of the board. And every pathway, or branch, is a single move that connects one board to the next.
All right, so let's really get into this. I think the best way to wrap your head around a game tree is to actually build a small piece of one, right from the middle of a game.
So we start with our current board. That's the root of our tree. It's Min's turn. And let's see, she has 3 empty spots to choose from. So from that root, we draw 3 branches, one for each of her possible moves. Boom, 3 new versions of the board. Now, from each of those, it's Max's turn. And if Max has, say, 2 moves in each of those scenarios, well, our 3 branches just split into 6. You can see how this thing just explodes outward with every single turn.
And here's the really crucial part. For a simple game like tic-tac-toe, that game tree, yeah, it gets big, but it's still manageable. A computer can actually map out and analyze the entire thing, following every single branch all the way to every possible conclusion. We're talking every single win, every loss, and every draw.
But just seeing the whole map isn't enough. I mean, how does the AI choose the best path? Well, to do that, it needs to assign a score to the end of each of those paths. It has to translate winning or losing into simple numbers. And the scoring system is, well, it's beautifully simple. From the AI's point of view, if Max, our X player, wins, that's a +1. If Min, the O player, wins, that's a -1. And a draw, that's just a plain old 0. So you can see the goal here. Max always wants to maximize the score, and Min always wants to minimize it.
And that brings us right to the heart of it all, the Minimax Algorithm. It's built on one incredibly powerful and kind of ruthless assumption. Both players are perfect geniuses. They will never make a mistake. Max, the maximizer, will always choose the move that leads to the highest possible score. And Min, the minimizer, will always choose the move that leads to the lowest.
So it's a constant tug of war. What's best for Max is the absolute worst for Min, and the other way around. When it's Max's turn, she's looking at all her options and asking, which one of these moves gets me to a +1? And when it's Min's turn, she's doing the exact opposite, thinking, how can I force this game down a path that ends in a -1?
Okay, now here is the really mind-bending part. The AI doesn't start from the current board and guess what might happen. No, it starts from the future. It looks at all those final scores, all the +1s, -1s, and zeros, and it works its way backward, up the tree, calculating the value of every single move based on where it will inevitably end up.
So let's try to think like the algorithm for a second. Imagine it's Max's turn. She looks at her choices. Path A is a guaranteed win for her, a +1. Path B is a guaranteed loss, a -1. I mean, which move is she going to make? It's completely obvious, right? She's taking the path to +1 every time. The algorithm is just that simple logic, applied over and over again for both players.
And that brings us all the way back to our initial mystery. Why was Max so upset? Because she was thinking like an AI. She saw the whole game tree in her head. She realized that no matter what she does, even making that obvious block, it starts a chain reaction. A chain reaction where Min, playing perfectly, can always force a win. Every single option she has, every single branch on that tree ultimately leads to a -1. She's completely trapped. She hasn't lost yet, but she knows her loss is absolutely inevitable.
All right, so Minimax gives us perfect play for tic-tac-toe. The logical question is, why don't we just use this for a much more complex game, like chess, and create a totally unbeatable AI? Well, the answer comes down to a huge problem of scale.
I mean, in theory, the logic is flawless. It should work for any two-player game where you have all the information, no hidden cards or dice rolls. But in the real world, we hit a wall. A massive computational wall.
Think about it. In tic-tac-toe, on any given turn, you have, what, a handful of possible moves? But in chess, the average number of legal moves from any one position, what we call the branching factor, is around 35. So with every turn, the game tree doesn't just grow, it absolutely explodes.
And just how big of an explosion are we talking about? Well, to look just 10 moves ahead, that's 5 moves for each player, an AI would have to check, get ready for this, over 2.7 quadrillion board positions. That number is just staggering. No computer on Earth can crunch that in a reasonable amount of time. Building the full game tree for chess, it's just not possible.
And if you think that number's crazy, don't even get me started on the ancient game of Go. The average branching factor there is about 250. The number of possible games of Go is literally greater than the number of atoms in the known universe. So yeah, Minimax on its own doesn't stand a chance.
So if the map is just way too big to explore, how did an AI like Deep Blue manage to beat a world champion like Garry Kasparov? The answer is, it cheats. Well, not really, but it uses a very clever shortcut. It makes educated guesses. And that shortcut is called a heuristic. A heuristic is basically just a rule of thumb. It's a smart function that can look at a board in the middle of a game, nowhere near the end, and assign it a score anyway. It's basically estimating who's in a better position, who's more likely to win from that point. And what's so cool about this is how human these heuristics are. They're often based on principles that human chess masters have understood for centuries. Things like material advantage. A queen is worth way more than a rook. Or positional control. Having your pieces in the center of the board is a huge advantage. All the AI does is turn these timeless ideas into a cold, hard mathematical score.
So here's how it all comes together. An AI like Deep Blue doesn't even try to see to the end of the game. It can't. Instead, it'll search, say, 10 or 12 moves deep into that massive game tree. And at the end of those paths, it just stops. It uses its heuristic function to give each of those final positions a score. And then it uses that exact same minimax logic we talked about, working backward from those estimated scores to figure out the best move to make right now.
And really, that's the whole story right there. For simple games like tic-tac-toe, you can use the perfect brute force logic of Minimax to solve it completely. But for these mind-bogglingly complex games like chess or Go, you have to combine that logic with these clever, almost human-like shortcuts to have any hope of navigating that impossibly vast universe of moves.
So that leaves us with a pretty cool question to chew on. When an AI uses these heuristics, these rules of thumb to figure out the best move, is that just cold, hard calculation, or is it something more? Is it a kind of logic that starts to look an awful lot like the intuition, the creativity that we think is uniquely human? It really makes you wonder where pure logic stops and something that feels a lot like real insight actually begins.